I'm Andrew Mangum. I'm a scientist, a computer scientist, who now works largely on the morphology and morphogenesis of plants and animals. This piece of artificial biological tissue, which we printed out, shows growth, where growth is being dictated by these patterns, and growth has followed two rules. One is that it will grow towards where the little red spot is, and the second rule is that the growth rate depends on the gradient, how fast this colour is changing. So it's growing a lot just here, it's not growing at the tip, just behind, then it's not growing here. So that's a simple rule. So what we've done is to take these rules and apply them, or explore whether they apply in biology. So we have a hypothesis that these rules occur, and now we're going to say, does that happen in biology? So for example, we took plants. Our team works a lot on plants and the shapes of plants. The classical one was the development of a snapdragon. So we're going to get to this, which is a model of a snapdragon that we've developed in the computer program. So what we're going to get is the relationship between these tentacles, which is a primitive morphogenesis in the form that Turing might have expected, and the much more sophisticated growth that biology has evolved to do. This relates back to Turing and his contribution, I think. His first paper was about computability, and he was talking about how if you can express it, you can, in principle, compute it. And it relates to his paper on morphogenesis, because we're actually now able, given the technology we have, potentially, I'm sure he would have loved, and he would have loved to have been able to do it, we can compute our hypotheses and predict therefore, based on these hypotheses, how, for example, a snapdragon shape might form. I suspect that the rules that we're building into this are common rules to all of biology. So to make real progress in understanding morphogenesis, and to translate the patterns that Turing talked about into the morphogenesis that he was speculating on, we have to have programs that will allow us to express what we want, what we expect to happen in terms that are consistent with the biology, but we have to solve those on a computer which understands computing. For that we have to write a large program, a million-word program, which captures everything about the physical world and allows us to use a new language of how developmental biology works. Difficult to say what Turing would have done. I think he would have been, in one sense, quite disappointed that he could not actually compute sort of more confirmation of what he'd theoretically come up with. So the hardware just took too long. It was fast, the development of the hardware was fast, but it was still long. It was going to be, as I say, it was going to be 30 years before anything really could be computed that would verify what he'd said.